Join me in welcoming Mark Johnson.
Okay, thanks, Stuart, and welcome everyone. Get a little. Okay. Well, yeah. So I guess I just found out that as part of the tradition of this gathering, to tell you a little bit about how I got here, which is sensible. And as I look back on it, I mean, how did I get here? It had a lot to do with stuff like you're doing right now. And so I'm going to talk about water today. We'll be doing some fun stuff with it, I hope. This is a video camera that's just watching what's going on in this black box. And we'll come back to that in about a half an hour and talk about what that really is. But just so you know, it's not a great mystery, you're looking at cosmic rays streaming through the building and running right through that box. And so that has something to do with electrical charges in water. So it's kind of a soothing thing to gaze upon as we go through this, I think. But they're viciously high energy particles that are doing that. And they're very tiny. And we have another experiment going on over here that we'll talk about in a second. So these demonstrations are not, unfortunately, for you to play with. And so I wouldn't want to encourage people to come up and do a hands-on with some of the apparatus that we have going on. But you're welcome to come up and take a look at the cloud chamber, because that's nothing but a cold box. How did I get here? Well, I grew up in Oakland, California, right? And class of 73, and that's a public, high school. That's a darn good public high school. And I got here because of a really inspirational chemistry teacher named Jon Fen. He was so good at teaching chemistry, they made him principal. And so he stopped teaching chemistry after I left that, unfortunately. But I got interested in doing chemistry and science because, well, of course, I was, I could see that you had to be, conscious of politics whenever you're doing science. We just had a big oil spill in the Bay Area from a tanker that crashed into one of the bridges. And so I had a science project on what oil does to things like the San Francisco Bay and so on. But I went on from that to this place. This is on the Berkeley Hills, right up above the hilly place. And so you look up when you grow up, and I grew up in the flatlands in the Bay Area, and you look up and there's this great, strange building up there. It's called the Lawrence Hall of Science. And that's where they took us when we were your age. And you went around and did little experiments and appreciated what people did in the national laboratory that's associated with this place. And it's this guy, actually. That's Lawrence. Lawrence Berkeley Laboratory, that's the Lawrence Hall of Science, that's Ernest Lawrence, and he's a New Haven guy, not making this stuff up. So it turns out he lived here, Whitney Avenue. You can drive up, if you're driving back up to Hampton, you'll go right by it. Just look over on the right, and that's Ernest Lawrence's house. How did he get from New Haven to Berkeley, you ask? We'll come back to that in a little bit. Okay, and so Lawrence did pretty well for himself with the laboratory that I visited. Was famous for this. And so many of you know that there are many elements that make the primary species we link together in chemistry to make molecules and so on. And so they, in fact, went out and discovered a bunch of new ones using an instrument that Lawrence built when he was at Yale. And so, unfortunately, because he built it at Berkeley, they got elements named after them. Berkelium, californium, Lawrencium has his own element, as it turns out. Unfortunately, no New Havenium or anything fun like that we could have had if we had managed to keep a hold of Lawrence. So that's how I got into this business. It looked like a lot of exciting things going on in science, and I learned a little bit about how they did these things. You have stuff going on in New Haven that's just like that. There are fabulously and powerful instruments that are in play a couple of blocks from where we're standing that Yale manages. And the one that I want to talk to you about today is called the Yale Proteomics Center. And I don't think they have tours for the public, and I haven't checked it out, but they should, because this business of proteomics is very powerful stuff for medicine these days. Many of you have heard, they can look at the genetic makeup of your particular body and then target remedies for disease, or anticipate you might get a disease by rapidly looking at your particular code and then targeting therapies for it. So proteomics is what that game is called, and we want to talk about how Yale actually did a lot to make proteomics happen. And that is a technical thing. It's not a biological thing. It's a highly technical, simple chemical process that started this whole revolution. So that's what we're going to talk about today, is what do you need in order to do proteomics? Well, okay, so we're going to look at molecules. molecules that are important in your body are big. H2O is a tiny molecule. We need that too. But the molecules that do the work to do all the biological functions that we enjoy, you can't, if you look at all the individual atoms, you just can't even see them in there. So this is an object, cytochrome C. And so if we want to think about the structure of that thing, it weighs 12,000 times the weight of a single hydrogen atom in a water molecule. So we're looking at a pretty big object. That's the sort of minimum thing you have to start looking at in order to look at biological processes. So we're done with water, right? So we're now moving on and trying to look at how we treat gigantic objects like this and know exactly what they're composed of to within one atom resolution. And so this thing, we'll talk about this, it contains 100 amino acid residues, and that's something we have to think about what's our amino acid residue have to do with anything. So you look at these loops and these colors and all that, but what's in each one of these is a molecule thing, and they're kind of, manageable. So this is an amino acid. It has an acid, this is the amine, and when you're in your body in a protein, they all link up by spitting out water molecules, and they make these really long chains, and that we can understand. It's just like you're snapping beads together and making it's very much like that. A protein is a long 100 or so bead necklace, and they're all different colors. And your particular bead that encodes your world is just, if I knew the exact ordering of all the colors, I would know everything I think there is to know about your particular body works. And so how are we going to get the decoding of the color sequence? Okay, so that's, now this is a very simple thing to think about. That's my amino acid bead, right? Each one of these is a molecule, and they're linked together by those peptide linkages. And so I just want to know what the order is. 1, 2, 3, 4, 5, 6. And so suppose that I broke it apart. If I physically took a necklace, and I just broke it in half, every which way you could possibly break it in half. Okay? And so if I broke it here, for example, I would see these two coupled together, and then the next 4. Or I could break it in another place or another place. And if I break it in all the ways you can break it, then mathematically understand the ordering of all the little pieces you got. You can uniquely recreate what your particular sequence is. That's what they do in the proteomics sense. So very precise breaking in and measuring of all the component pieces is the game of proteomics. How do you do that? Okay, you have a big molecule there, you break it, you break the necklace in half, and now you need to know what the 2 halves are. So if I did that in my house with necklaces, I might weigh the 2 halves, and that would tell me how much was in each one. So I could do weigh, that would be a good way that I might use in order, each time it broke, I would see 1 and 4, 2 and 3, weigh those each one at a time, and that would tell me where the thing broke. And the problem, of course, when you want to weigh something, if you want to weigh a physical object, you can use gravity in order to pull on it, and then you can figure out the strength of that force and use that to get the weight. But a molecule has almost no mass. Gravity isn't doing anything to a molecule. That's just right out. And so you need to have a big force that you can put on a molecule that you can do something with in order to use it to determine the mass of that object. So you still want to weigh it. Gravity's out, and it turns out that electricity's the ticket. So electricity is going to give you another force that you can use to move things around. All right? And so it's pretty. The basic thing to understand is not so hard. You have a positive in electricity. We have a positive in a battery. You've all seen the plus and minus on the batteries, right? The plus is going to attract. If you put an electrical charged object in there, and it has the same charge as one of the electrodes, it'll be repelled from it and attracted to the other one. It's not so hard to understand. And so if I have an electrical charge and I put it in between a positive and a negative region, it'll just run away from it. It'll be accelerated towards the electrode that has the opposite polarity to the charge that I put in. So electrical forces can push little molecules around easily. And it turns out that gives me enough information in order to weigh them very accurately. So the game plan is I wanted, and so if I really want to do proteomics on a necklace of amino acids, I'll need to put electrical charges on it in order to use my charging game in order to measure what the weights are. So I'll just put plus on each amino acid. And then if I broke it apart, the two pieces that I got would both have electrical charges, and then I could use the motion that I can induce in those charged things in order to weigh each one independently. It's as simple as that. Except it isn't so simple because these molecules are not so easy to put a charge so happily on each one of the amino acids. It would be a very hard thing to do. You could be child's play to weigh these things out and measure their composition. So how do we do that? So it turns out fast-moving ions, so an ion is a thing that you call, any object that has an electrical charge has a name. Call it an ion, okay? Ionic objects are that plus thing in here, so that has now had an electrical charge on it. And so if you have a very fast-moving charged object and you just smash it into a stainless steel plate, well, it smashes into it and the fragments come out of it that turn out to be very easy to detect. And so I can detect them very efficiently. I can use electricity to weigh them, but there's a catch in that I need very, very low pressure. We're living in atmospheric pressure right now. That's a very dense, viscous medium. You see professional tennis players or golf professionals. They're using the viscosity of the air in order to twist the ball to fly through it. They're using friction. The friction through the air is very useful for sports. Really bad to weigh molecules because you want to push them with that electric field, but then as they swim through the air, they're losing their push that you gave them when you started the process off. So you need to get rid of all that air. So you need a very, very low pressure environment in order to weigh things out. And that makes everything much more difficult. It's a billion times less than the Earth's atmosphere is what you need in order to get this. Okay, so when you do that, and you get objects that look like this. This is what's called a mass spectrometer. It's a thing that weighs things out using electricity. And it's a big cylindrical metal thing. And it's like that because you got to get rid of all the air inside of it. And so you got to pump it out in order to get this thing to work. And so we have one of these, and they have a bunch of these down in the proteomics center at Yale and so on. And they're really good. And so when I was in high school, we learned that there were the weights of the molecules, for example. And these both weighed 28 in the calculation that I did when I was in high school chemistry. And because they have the same numbers of protons and neutrons. But if you weigh them out with a modern mass spectrometer, the spikes here is how much something weighs, and this is going from 27 to 28. And so within that, what I thought was only one mass unit was good enough for me, is actually the precision with which similar molecules are different and that it can be measured is profound. So to put some numbers out, 1 part in a million to measure the absolute mass of a molecular object is trivial. So that's it. That's their daily routine that we do down at the Keck Center at the moment. Okay, so we can measure it. All we have to do is get these things in an environment without any gas around it. And here's the problem: all the molecules that are worth anything in my body are absolutely dependent on being in it. And that means that they're in a water environment. Most of your body's water. And those big molecules that I was just talking about, the proteins and the DNA and all that stuff, it's got to be in the water. It's like a fish out of water. You take the stuff out of there, it is a very unhappy object, right? Intrinsically needs to be in that solution environment in order to exist. And so this is bad. If I could just get it out and get rid of all the water and put it in an empty vacuum, I'd get the weight absolutely perfectly. And so everyone knowing this for 40 years at least said, well, gee, it would be great if we could just get these molecules and use a mass spectrometer. We'd be off to the races. People have known that forever, and no one can get them out. It's a simple engineering problem, but it stalled the whole field. Okay, so let's think about this. The problem is big biological molecules, like DNA, are only present when you have water. So why don't you just take it out? Turns out that the energy that it takes to pull a protein molecule out of water is much larger than the energy it takes to break it in half. And so you're stuck. Right? If I want to reach in there and grab somebody out of the audience and have a whole family come out together, I keep ripping you out of the center row, and they're hanging on as hard as they can. But I keep getting only one of you out because the strength with which you're held together is less than the energy it takes me to pull from the outside in. So you look doomed in order to figure out how that seems like an intrinsic problem. You're never going to be able to beat it. Well, it didn't stop people from trying. So what people did is they took some protein and they dried it out, freeze-dried kind of thing. So you just pump it out. And so you didn't ask to get ripped out of the water. You just evaporate the water away, and now there's this dead protein molecule sitting there on a microscope slide. Right? You still got to get it from there up into where it flies into a vacuum chamber. So what people did is they just whacked the surface with a high-energy particle and blasted stuff off the surface of it. This was a desperation move, must be said. And so it had a name, though. It was called fast atom bombardment, or FAB. And so that was the main technique used in places trying to become the proteomics center for decades. I like to think of FAB like this. It would be like trying to measure something delicate, like, maybe flowers or something growing on the desert floor by whacking it with a meteor. It's not a good way to subtly get these delicate objects up into the atmosphere, right? And it sort of worked, but very few of the intact species actually made it off of the blasted surface. All right. Yale scientists figured this out. I had nothing to do with it. I'm just the messenger here, okay? But they are friends of mine, and I think it's nice to think about how they beat this problem. And they did it by thinking about how charged particles move around in liquids. It has a lot to do with understanding how water interacts with electricity, and that's the title of our talk today. So electricity doing something with ions, charged particles moving around in water. The properties of that are all you need to know if you think carefully in order to in order to overcome the problem of pulling intact molecules out of solution. All right, so let's think about some ions moving around in water. Turns out this has been done for a long time. Just right after electricity was discovered, 1790, William Nicholson, for example, did an interesting experiment. And so I guess it's cooking for those of you in the front row. Maybe we can take a look. Maybe we can, come on up, we can take a look. You need to report back on what we're seeing on our first experiment. What do we got here? No, we're not going to get into any of that stuff. It's not harmful anyway. But what do we see? Yeah, what is that? And so what's going on at the top? The water is like lower here than here, right? And then what do we mean? It looks like maybe bubbles are running up there. Bubbles are starting off down at the bottom, they're running all the way up to the top. When the bubbles get to the top, they push the water down. There's twice as much air on this side than that side. Yeah, see? Okay, so thank you, gentlemen. Appreciate it. And so what we've just seen, of course, is the famous experiment of the electrolysis of water. That's using electricity to take H2O and turn it back into the elements from which it came. You get 2 hydrogen molecules and 1 oxygen molecule when you electrolyze water, which has been known for a long, long time. Now, if you take the gas that we just generated and you put them in a balloon, which we have done, we'll take the gas that comes in this balloon, for example, and Aaron Watt is going to tell us a little bit about the properties of those gases that we just created.
Okay, so what I have here are some balloons of gas, the same gas that is being formed when we're splitting this water apart. And so we notice that on one side there appeared to be more gas than the other side. Well, the gas, there's more of it, that's the hydrogen. We know water is H2O. We're splitting water on this side into hydrogen. The other side that's only half as much volume, that's the oxygen. So what I have here are balloons of each one of those gases. The first one is oxygen. This doesn't float in the atmosphere, but this is full of pure oxygen. What I want to do is blow this balloon up and see what happens. So first off, I'm just going to be doing oxygen. All right, so I bring my little candle up. I want to see how it burns. This is a normal balloon. I think, no, that's how normal balloons pop, not very exciting. However, we can make it a little more exciting when we look at the hydrogen. So hydrogen, we can see, is lighter than the atmosphere. And it gives when we think of burning, we usually think about something that burns into black, right? It burns back into carbon. Well, this is just hydrogen in here. When we burn it, it actually turns right back into the water. So let's see what happens when I do that. So we can see a little more exciting of a burn there. What's neat is that I actually, I got another one here. It's a little bigger. I actually blow that one up as well. All right, before I do this, the really neat thing is that we think when our car burns gasoline, we know it makes carbon dioxide and other pollutants. When I burn this balloon, it's actually just making water. I'm forming the water all over again. So here we go once again. Take a look on the screen when this happens as well. Cool stuff.
All right, thank you, Eric. Little electricity, little water, you know, science. All right, so that was done, as I say, a long time ago, watching how the interesting things happen when you do that. And that's the experiment that we just saw. So our front row in the audience verified that we had different levels of gas that was made when we passed the voltage over. It's a very low voltage, actually. And of course, Yale, you may have heard in the news, Yale is just starting the Energy Institute on the West Campus. And that has everything to do with learning how to do that on the grand scale, with taking light from the sun and turning that water back into hydrogen, and then turning that hydrogen into methanol, and finding a way to make fuels that don't yield a net CO2 production in the atmosphere and are renewable. So that's a big deal on the Yale campus, and there's a lot of effort that was already here, and now it's been formalized in a new thing that's going on in our community. Okay, the next thing we need to understand in order to get our head around proteomics is water just by itself does an okay job of interacting with electricity and turns it back into its elementary gases. But if you take something and put it in water, well, we're going to put proteins in water, but let's start small, start simple, and put an acid, a hydrochloric acid. We're going to put that in water and see what it does. Well, we know that acids are bad for us, right? You can burn yourself with acids and so on, so we don't want to get too close to this demonstration. So, and we're going to use salt instead of hydrochloric acid. But the guys figured this out. We're talking 1884. This stuff's been around forever, and I'm going back to the archaic literature here to show that any of these people could have put proteins in the gas phase and done proteomics 100 years ago. It's trivial when you see how to do it. No one was thinking about the experiments that we all learned in high school. Okay, so let's look at what electricity does when you actually put something in it that separates itself into charged particles. Aaron's back by popular demand.
All right, so I've got a light bulb set up here. I'll just prove to you that I can still make the light bulb turn on easily by moving this clamp together. So the electricity has to travel through this clamp for the electricity to go, but then when it's open, no electricity goes through it. All right, so we know that when you go to your favorite swimming pool, if a thunderstorm's coming, they kick you out of the pool because they don't want you to get electrocuted. But if there's a way to find a pool that had really pure water, I think you'd actually be pretty safe. So let's see what happens when I place this clamp, which when there's a connection, the light turns on, into pure water. Huh. I think we all think of water that it conducts electricity, but it actually doesn't conduct electricity well at all when it's pure. So I can prove once in the water, I press it together, the connection's still there, but electricity won't flow through water on its own. Let's think of another thing. We all know about sugar, right? Sugar water, it's like almost lemonade. Let's see if maybe would you be safe or not if you swam in a pool of lemonade? All right, so I'm going to pour a lot of sugar into this water. Mix it around, do my best. When I put sugar in water, it still doesn't conduct electricity. That's pretty interesting, maybe a little different than what we would expect. Light bulb's still working, sugar water won't conduct. All right, so now I have another thing of pure water, still not conducting electricity. Instead of adding sugar, I'm going to add a salt related to that HCl that he had up on the board. So what I'm going to do here is do my best to put the tiniest bit of table salt in here, see what happens. Maybe turn off the lights to make this a little more clear. We need to drama. Yeah. All right, so light bulb is off. Let's see what happens when I put a tiny, tiny bit of table salt in there. I don't want to overload, I guess. All right. So a tiny, tiny bit of salt in there. Nothing yet. A tiny, tiny bit more. So I put just a dash of that salt in there. It's kind of now I add more and more to it. Magic, right? So this salt sounds like it's different than the sugar. It's saying that we have different kind of molecules. A sugar is a different kind of molecule than salt. Salt, if you swim in the ocean, it's certainly not safe when there's a lightning storm because that'll conduct electricity. But if you're in an ocean of sugar water, I think you'll be all right.
All right, Aaron, thank you again. Okay, so we have so what we just saw going on there is what happens when you put salt into water. The sodium chloride separates the sodium from the chlorine, and the sodium becomes positively charged, and the chlorine becomes negatively charged. So those are those charged things I was talking to you about way back at the beginning. And if I have charged objects and I put a positive, just like you saw in our lecture demonstration, one of these is positive and the other is negative. The charge is run to their respective electrodes because they're swimming independently in the liquid solution. That's what you need to know. You dissolve salt into water. It looks white. They both look white. They look the same. But one of them has the property, when you put it in water, it does not separate and make charged particles or ions. And in the other case, in sugar, and the case of salt, it's great at breaking apart and make 100% of it goes to these charged things. And you can use it as a wire, in fact. It's such a good conductor of electricity. Okay, so we have those independent ions swimming around. So now we understand the experiment we just did is this. If I put salt into water, the positives and the negatives are now moving independently. If I put electricity in play, it'll attract the opposites. And that was the conductivity we saw, was the swimming of the electrical charges towards their favorite electrode in opposite directions. That was what was conducting electricity. Okay, so people have known this since 1888, as I pointed out. And so what was stopping them from using this knowledge? Turns out, before I go on with that, Yale in the 1930s was very interested in these properties of how charges interact with water. And I don't know, so this is a picture of our 1930s era Yale chemistry department person, Herbie Harned. I don't know that anybody's heard of Herbie, it's not one of these Einstein kind of names, appreciate that. But Harned is the guy that many of you may have heard out there in the high school, types, that the neutral pH of water is 7. Anybody know that fact? pH 7, neutral water. It means you can't get, pH is the amount of hydrogen ion that's in the water, and you can't get rid of it. And that's why it didn't conduct very well, because it's tiny. It's a tiny amount at neutral water pH, right? And so Hardin's the guy that measured that number in 1934. He did it using electrochemistry. And so we built into everyone's life, a little math must fall. But we're not going to go into that today. All right, pH 7 neutral water is a Yale thing, as it turns out, from Hardin. There's another Yale player in this equation, and this guy, John Zeleny. He was the chairman of the physics department at Yale in the 1920s. Now, Hardin is well known around New Haven as, remember I talked about my hero when I was in high school, Ernest Lawrence, got an element named after him. Zeleny fired him. He was the chairman of the physics department who didn't see any value in this technique that Lawrence was building up. Or at least I'm blaming him for letting it happen in the context of, an excellent guy going out west. So, but that's not why we bring Zeleny up, to remind ourselves of the painful past. We bring Zeleny up because he's the guy that did a very curious experiment. You ask yourself, why would you even do this experiment? And what he did is he put a syringe, and we have a syringe for you up here. That's the needle of the syringe that's pointing out.
It's for bleeding water.
Yeah, that's right. It's got a little bit of a drip going on there. And so this is the same thing. This is just a syringe that we got from like the health center, and it's getting pushed by a motor, so it's just continuing to drip a little bit. And what Zeleny did is he put one electrode on one side in the water. Well, he put two electrodes that just conduct. We just saw that. But then he put the other electrode outside the water. Curious thing to do. If they were both dipped in, the ions would run back and forth, light bulb with light, that'd be the end of it. So now I told you it's hard to pull those ions out of there. And I was abusing my third row in order to make that point. And so what happens if they still obey the laws of electricity? Positives want to go one way, negatives want to go the other way. I turn on the electrical force, and the negatives can go, and they can interact with the positive electrode. The negative electrode will draw the positive stuff until they all get to just the skin of the surface, and then they stop. Right? That's what's going to happen. Has to happen, because it's too hard to pull those things out of solution. We already went over that ground. But that didn't stop Zeleny from persisting, and he kept turning up the voltage. So he turned up the voltage a little bit at a time, and when what starts to happen, and so we'll see this ourselves in just a second. What starts to happen is all the positives get pushed together, and they all start to push the surface of the liquid away. You turn the voltage up a little higher, the force becomes stronger. You can push them so hard that they break off a drop. You overcome the surface tension. The drop's still there. All the ions are in it. You never ask the ions to get out of the water, because that's a bad thing. We already talked about that. But now I have an object that's flying through the air that has halfway to what I want. It's got DNA molecules on the inside, water still surrounding them. Now my job is just to get rid of the water, and that's the next thing we have to talk about. So Aaron, why don't you show us what happens, the curious thing that happens when electricity hits the surface of ions in water.
All right, so up on the screen here we have a needle. Just like you go to the doctor and you get a needle stuck in you. This is the same kind of thing. And there's a drip of water coming from it right now. And you can see it dripping there, and it's basically just falling straight down, right? Because we haven't connected the electricity yet. But if I turn on the electricity, we can start small, and we can watch what happens to the droplet. And you can get the lights, maybe see it a little bit better. All right, so it's just dripping. We'll bring up the electricity. And pretty soon it's not going to be dropping straight down anymore. It's going to be kind of going out to the right. And so those are the charges running away from the needle. We can keep going up.
What voltage are you at there, Mike?
So right now we're at about 3,000 volts. Should we go a little higher?
No, there's no current.
All right, there's 4,000. 5,000. Okay, we'll go to 5,000. Well, there's 5,000. Should we go a little bit higher? Yeah. All right. Here comes 6,000. Should we go a little bit higher?
Oh no!
All right, so there's 7,000 volts.
Okay, better start taking that sucker back down before something bad happens. All right, so look at this thing fan out like that. These all started off as these little droplets that were running away because they were positively charged, right? And they were drawn towards the negative electrode. The entire drop is flying across the gap, carrying the water with it. Okay? Now the reason it's fanned out like that, think about that for a second. Why would it have that curious shape? Maybe you can drag it back up just so we can watch that one more time. So it's not a drop anymore. It goes to this fan pattern. It's a very, very, very fine mist when that happens. All right? And the reason it's fanning out, can anybody guess? Why would it do that? Why would it become a great large? Yeah, back in the back.
Because the positive ions are repelling each other.
Oh my goodness! What's your name?
Ken?
Were you coached? No, that's a brilliant answer, and it's exactly correct. So, round of applause. Sign them up. All right, so all these little droplets are coming out, and they're all highly positively charged, and they want to run away from each other. And it's easy to see that, because look at them run away. Right? They're all spanning out to get as far away as they possibly can. Thanks, Mike. Mike Camrath is our man on the spot today. And so that's a curious thing that a lot of us didn't see coming. And so that has very interesting properties to work. That was 1928. Okay, proteomics didn't happen until 1992. But it's the same effect. So all they do down at the proteomics center is that. Right? They make what's called an electrospray. An electrospray is a way to grab things out of solution and keep enough of its native solution environment around that it remains happy as it flies through the air with the greatest of ease. And here they are flying away. So it has all people study these structures, and I've lost my it's okay. Not my first rodeo here. No, we got another one. So the electrospray is what we're talking about. And so there are nice pictures of how these things can be manipulated and so on. And there's a whole engineering that's associated with manipulation of that effect. Okay, so the first person that tried to put big molecules that would not survive extraction up into the gas phase is this guy, Malcolm Dole at Northwestern, 1968. If you think about this, in 68, man on the moon, 69, I mean, real big stuff's happened, discovery of DNA. Meanwhile, we're still toiling away trying to figure out any molecules to come out of that solution. And Dole tries it. And he had an apparatus, and he wrote, in science we fill up these thick volumes of the scientific literature that almost nobody reads and so on. And this one is, volume 49 in page, a few thousand or some, Journal of Chemical Physics. He wants to see macro ions. That's the name he used for these large things that don't want to come out of solution. And the idea is to keep breaking them apart. It's a fractal kind of idea. If the charge starts to evaporate, his idea was if you evaporate the water around all the charges. You think about that. You take 5 friends who don't like each other very much, and they're all standing as far as they can from each other. And then you say, okay, everybody take 1 step forward. You are now much closer to the people that I've told you're not happy with. And then you take another step forward. And you're touching. Ew! You're touching each other. Horrible. And so it'll break apart all by itself. The act of evaporation forces the charges to go into a repelling environment. And then they just split out. They split until you're finally down to 1. Happens very naturally. 1 charge. You just stick an alligator clip from Radio Shack on the syringe from the health plan, and you get one ion that comes out of this thing, no matter how big it is. So DNA works. It worked in 1928. It worked in 1968, and still nobody got it. Like, what was stopping them? And this is the last little Yale thing I want to share with you. In his paper, and this is slightly technical, but I think it's valuable to go through it. He weighed them. He got these things into a vacuum, so he had pure trajectories, weighed them perfectly, and they were not the weight of the thing he put in. He knew what he put in by another method. He did all this work, got it out, weighed it exactly, and it's not the same stuff. So that's disappointing. Malcolm Dole never figures it out, right? And in that paper, however, he said, whoa, it doesn't, everything worked just like I thought, but it doesn't work, and I don't know why. And in that paper, he referenced this guy, Jon Fen. Right? Jon Fen was on the chemical engineering faculty at Yale, knew nothing about or cared about biological molecules and gas, phase, any of this stuff. What he knew about is rocket engines. He was a guy in World War II that worked on the chemical engineering of burning rockets. But he got his PhD, get this, he got his PhD with Harned at Yale, the guy who did the neutral pH measurement. So he knew about this electrical stuff quite outside of his new love, which was rocketry. So let's just pause for a moment and get to know our hero of our story, Jon Fen. So he arrives at Yale and starts doing his research, working on his doctorate in chemistry. Pretty exciting times? No. We were assigned to our advisors. I recall Herbie, that's Herbie Harned, as he was known but not addressed, saying to me, Fen, you might as well go work with Gus Akerlof. Akerlof's kid went off and won the Nobel Prize, actually, in economics. He's at Berkeley. But this is what it was like at Yale at that time. Obviously, I was something less than inspired by this introduction to original research. The experiments were a boring, pointless chore with few redeeming features. The results contained no surprises and nothing of much interest to anyone, least of all me. Now, that's not the kind of alumni report you like to get from the PhD candidates in your institution, all right? And he was very outspoken about that. Much of the research by Harned and his colleagues was on the properties of electrolytes, that's ions in water. The more dilute, the better. So narrow was this focus that when I left Yale halfway believing that physical chemistry was the study of slightly contaminated water. Okay, so it worked out okay for John, as you'll see in a second, though. And so in that, why did Malcolm Dole reference Fen? He's got nothing to do with this story so far. Turns out it was the rocket stuff. Dole had an idea that somehow they weren't drying out. And that was the problem. Couldn't get rid of the residual solvent. And so Fen knew about how gases rushing through small holes or apertures, that's what a rocket is. You have fuel burning through a tiny aperture that then propels the rocket. And every time, you ever seen a picture, you look up in the sky, there's a jet airplane. Behind that jet airplane, what do you see? White. What's white? Ice. Right. It's crystals of ice that are forming from the moisture in the air, or the fuel that's burnt by the engine. And so the spontaneous formation of a droplet in humid air is what Malcolm Dole was accidentally finding out. And Fen knew that if you have very, very cold gas, ions love to attract the surrounding water vapor into droplets. They spontaneously form a drop. And that's what our little demonstration's about. So there's a little rocket engine that Fen might have worked on, and so in the plume of that rocket exhaust, you get a stream of little droplets that are coming out. Now that's why we have our lecture demonstration, which is our last thing to think about in this part of it. Is what we're looking at here is called a cloud chamber. So a cloud chamber is these were very common in the 60s. When I went to the Lawrence Hall of Science, I saw a cloud chamber. High-end nuclear physics is no longer in vogue, so I don't suppose they take high schoolers off to see cloud chambers anymore. So I'm bringing one to you because they're fun. And so what are we looking at here? The drawing. You come up and look at it after the lecture. What I'm doing is making a cloud in the box. It's kind of fun, right? And so what we've done is we've taken a cold bottom, that's dry ice. I think we're all familiar with dry ice, CO2. And so that's colder much colder than water ice. And then I have alcohol, like the kind of alcohol you can drink. That's forming a vapor because the top plate is hot. But then as it goes down towards the cold place, gas gets colder and colder. And as it starts to get cold enough, it reaches the dew point, and then it starts to rain. And you're seeing the rain, the little droplets you're seeing is a very fine mist of rain of alcohol that's coming down. And there is the point. And so if we study this cloud formation, like if we look at it for a couple of seconds, we might be able to find one. And so, and I won't wait. There was a little one track that went there. You can see a little, there's one up there. If you've been watching, that's an imperfection in the glass. If you've been watching this thing, you will note that occasionally there are brilliant streaks. There was a streak. So there, okay, you guys believe it? There's like streaky stuff happening. All right? Very rare. Occasional streaks. Any idea? Then I gave you a clue from the beginning of the lecture, right? So what we're getting, I think many of you heard about it's bad to be going to Mars when you have like a sunspot. Have you heard that stuff? So you get, and pilots have trouble when they're up in the atmosphere because they get exposed to radiation that we're not shielded from by our atmosphere. This is the radiation that we're living with every day. They're cosmic rays, very, very, very high energy, small particles that came. The thing you have to get about this is the particles came through the roof of the building, came through the ceiling, went through the box, and then you can visualize them. Why? Because the particle is moving so quickly through this vapor that's trying to make a cloud that what it does is it knocks an electron off of an alcohol molecule, and that makes it an electrically charged thing. But this particle coming from the cosmos is so high energy, it didn't even notice. It's clueless. It goes through and knocks off an electron from you, and you, and you, and you. And along that line, each one of you then gathers up a solvent drop because the vapor that wants to make a cloud loves the ion as the place to seed that cloud. So it's a trajectory of a cloud seeding that you're seeing from cosmic ray radiation that is causing a macroscopic droplet to form by introducing an ion along its trajectory. So that's a cloud chamber. And we've seen lots and lots of alcohol molecules have clung on to a little ionic center and started that process of cloud seeding. So Fen realized this in 1969, and it took him 10 years to dry out the drop. He reasoned that the reason no one's getting the right mass is you simply have to put in a way to drive off the water vapor. And it couldn't be simpler. In the end, after 10 years, what works? Well, you take a hair dryer and you heat up a tube of like copper that you might use in your house for a refrigerator or something like that. And you just pass these droplets through it, and as they get heated up when they go through it, it evaporates them all down to where they have their lone single biological ion is all that's left. So Fen put a drying tube on a 1928 experiment. That's it. And when he did it, cytochrome C comes up. Just remember I showed you nitrogen and oxygen measured with great precision. We weighed those out. Now you can weigh out an object that's 20,000 times bigger than that with the same precision. No problem. No ions left on it. You get exact composition of these gigantic species. So that's what they do down there is they get your stuff out of your body, they put it through an Electrospray, and then they sequence how you're put together using this simple technology. Does it have an impact? Let's think about that. The date is California, 1995. It's Los Angeles, Superior Court. It's the Simpson matter. Okay, so let's talk about, what has Electrospray done for us? What technique did the FBI use? Many of you are as old as I am will remember it all came down to the DNA evidence and it was all these things. How did they get the DNA evidence? The FBI used a method where the liquid goes through a very tiny but moderately long piece of glass capillary. That's Fen's drying thing. It has it is a glass tube with a tiny, tiny opening and a tiny run. That is heated and has applied to it a very high voltage and a moderate percentage of high electricity. I have no idea what that means. That's a court record of this thing. That's why it's called Electrospray. And so that's what, if any of you are seeing NCIS, anybody watch NCIS out there? What's Abby doing with his mass spectrometer and his finding out who the evildoers are? She's doing this with an electrospray that came to us from Jon Fen. The one thing I want to leave with you is the main thing about electrospray is that it does the magic job of taking anything you have in liquid and stripping it out of the liquid non-destructively. Jon Fen was rewarded with a Nobel Prize for his efforts in 2002 and is accredited with being the father of proteomics, even though he himself didn't care a whit about proteomics. And so the epilogue here is a casual reference to a paper, that was Malcolm Dole, to an unrelated field, relayed by a colleague in another department, was the key to the whole thing happening in '68. Nobody trying to solve the problem of pulling the molecules out had any idea that this was going to be the way to do it. So directing the effort to the answer you wanted didn't allow that there could be accidents that would be the key to the whole thing working. And here's what I love about this thing is once you know it, everyone can do it. It's hard to make money on it. It's simple and cheap, and it works perfectly well. Thanks for listening, and I want to bring up my helpers who put together our demonstrations, and we'll give them a round of applause. Rachel Ralph, Chris Johnson, where's Chris? Aaron Beck, Mike Camerath, and Helen Girardi.